course on probability and statistics. This is an introductory course, or you can say a first course on the probability and statistics, and it is quite useful for all branches of science and engineering. So, this will always exist. They are called monotone sequences. So, we say that a sequence En is said to be monotonic increasing if En is a subset of En plus 1 for n is equal to 1, 2 and so on. In a similar way, we define En to be monotonic decreasing if En is a containing En plus 1 for n is equal to 1, 2 and so on. Let us consider some example here. Let En be the interval, say 0 to 1 by n. Then En is monotonically decreasing sequence. Further, we can consider the say sequence En is equal to interval say minus n to n. Then En is monotonically increasing. One important result which is true for the monotonic sequences is that the limit always exists. I will state it in the form of a theorem here. If En is monotonically increasing, then limit of En is equal to union of En, n is equal to 1 to infinity. In a similar way, if En is monotonically decreasing, then limit of En is the intersection of the sequence of sets En. To look at the proof, let me prove the statement 1 first. If we take the En to be monotonically increasing sequence of sets, then the union En will be same for all m, and therefore limit superior will be same. Let me explain it further. If we consider limit superior of En, then it is equal to intersection union En, n is equal to m to infinity, m is equal to 1 to infinity. This will be equal to simply union n is equal to 1 to infinity, since union En n is equal to m to infinity will be the same for all m as En is subset of En plus 1 for all n. Further, if we look at limit inferior of the sequence, then this is union intersection En, n is equal to m to infinity. Now, in the intersection En, this is starting from Em plus 1 intersection Em plus 2, etc. Since the sequence is monotonically increasing, the first set in this sequence is the smallest set, and it is contained in all the sets which are coming after this. Therefore, the intersection will be equal to the first set itself, and therefore it is equal to Em. That means we are getting limit infimum as also union of Ems. If we combine these two results, the limit exists and it is equal to the union of the sets. The proof of the second statement can be given by direct argument, as in 1, or we can use De Morgan's laws. Let me state as exercises a few more results which are related to the limit of the sequence of the sets. For example, if I consider limit superior of a sequence of sets, and if I take complementation of that, then it is equal to limit inferior of the complements of the sets. In a similar way, if I consider limit inferior of the sequence of sets and I take its complement, then it will be equal to the limit superior of the complements of the sets. The proofs will be almost trivial if we make use of the lemma 1, which gave the representation of the limit superior and limit inferior, and make use of the De Morgan's laws. An extension of this exercise would be, if I consider f minus limit infimum of the sequence En, then it is equal to limit superior of f minus En. In a similar way, if I consider f minus limit superior of En, then it is equal to prove, say, the first part of this, we can consider f minus limit inferior of En, and let us write down the representation of the limit inferior in terms of unions and intersections. N is equal to m to infinity, m is equal to 1 to infinity, and at this we just use a set theoretic notation where a minus b is equal to a intersection b complement. So, this becomes f intersection union intersection En, n is equal to m to infinity, m is equal to 1 to infinity complement. That is equal to f intersection union En complement if we apply De Morgan's laws. Now, at this stage we can apply the distributive properties of the unions and intersections, and this will give us intersection m is equal to 1 to infinity union n is equal to m to infinity f intersection En complement, which is equal to intersection union f minus En, where n is equal to m to infinity, m is equal to 1 to infinity, and this is nothing but the limit superior of the sequence f minus En. In a similar way, we can prove the statement 2 of this. There are certain relations which include the characteristic functions of the limit superior and limit inferior, and I will state it as a statement in the following exercise. Indicator function of the limit inferior of a sequence of sets is the limit infimum of the indicator functions of the sequence of the sets. In a similar way, if we consider indicator function of the limit superior, then it is equal to limit superior of the sequence of the sets we may look at the proof of, say, one of them. Consider, say, x belonging to E star. Then this implies that x belongs to En for all but finitely many values of n. This implies that the indicator function of the set En is 1 for all but finitely many values of n, which is equivalent to the statement that limit infimum of the indicator function chi En x is equal to 1, and these statements are both if and only if. Further, if I consider x not belonging to E lower star, then this will imply that x does not belong to En for infinitely many values and this implies that limit infimum of chi En x is 0. In a similar way, if we use the definition of the limit superior of a sequence of functions, then we will be able to prove the second statement. A useful relation which is used for in set theory is that of symmetric differences. The concept of symmetric difference is defined by A delta B is equal to A minus B union B minus A. So, you can see here that it is A minus B and B minus A both are combined together, and that is why it is called a symmetric difference. And an equivalent interpretation for this is A union B minus A intersection B. From the Venn diagrams, we can see that if I have two sets A and B, then the symmetric difference is the shaded portion. Certain relationships which are true for set theoretic operations are given in the form of exercises below. prove that E minus F is equal to E minus E intersection F. It is equal to E union F minus F. E intersection F minus G is equal to E intersection F minus E intersection G. E union F minus G is equal to E minus G union F minus G. E minus G intersection F minus G is equal to E intersection F minus G. E minus F minus G is equal to E minus F union E intersection G. E minus F minus G is equal to E minus F union E intersection G. E minus F intersection G minus H is equal to E intersection G minus F union H. Certain relationships which are true for the symmetric differences are given in the next exercise. For example, symmetric difference of E with F is same as symmetric difference of F with E. Symmetric difference satisfies associative property, that is E delta F delta G is same as E delta F delta G. E intersection F delta G, it is equal to E intersection F delta E intersection G. That means intersection and symmetric differences are distributive. If we consider the symmetric difference of a set with the empty set, then we get the same set. That means as a group theoretic operation, empty set acts as an identity operator. If we consider with the full space, then I get the complementation. If we consider with itself, then we get empty set. That means with respect to group theoretic operation, E is its own inverse. And if we consider E delta E complement, then I get the full space. So one can ask that the class of all subsets of omega forms an abelian group with respect to symmetric difference operation. Further, if we consider the indicator function of the symmetric difference, then it is equal to the absolute difference between the indicator functions of the two sets. An alternative way of telling it is that it is equal to chi E plus chi F, where the sum is taken modulo 2. An additional exercise in this direction can be that if we consider A, B, C and D then A delta B is equal to C delta D, if and only if A delta C is equal to B delta D. In order to prove this statement 5, we proceed as follows. We show that either equality is equivalent to the statement that every point of x is in 0, 2 or 4 of the sets A, B, C, D. So let us consider x to be any point in the space omega. Then there are 5 possibilities. Let us consider these possibilities. One possibility is that x belongs to none of the sets. If x does not belong to any of the sets, then with respect to this point, A delta B and C delta D, they must be equal because x is none of them. If we consider x belongs to exactly one of sets, say x belongs to A, in that case A delta B will consist of the point x and C delta D will not include this point. If we consider x belonging to any two sets, let us take x belongs to A and x belongs to B, then clearly x does not belong to A delta B because the points which are common to both are excluded from the symmetric difference, and x does not belong to C delta D. So A delta B will be equal to C delta D. Let x belongs to A and x belongs to D, then x will belong to A delta B and x will belong to C delta D. Let us consider the possibilities that x belong to any 3 sets, say A, B and C, then x will not belong to A delta B and x will belong to C delta D. If we consider x belongs to all 4 sets, then clearly x does not belong to A delta B and x does not belong to C delta D. Thus, we have proved that every point of x is in 0, 2 or 4 of the sets A, B, C, D implies statement 1. Similar statement holds for B. Hence, A and B must be equivalent. To end this class, we look at one or two more examples of the limit infimum, limit supremum, and let En be equal to 0 to 1 minus 1 by n semi open interval if n is odd, and it is equal to 1 by n to 1 if n is even. Then if we look at limit inferior, it is the open interval 0 to 1. If we consider any real number between 0 to 1, then we can always find a capital N such that the point A will belong to both 0 to 1 minus 1 by n and 1 by n to 1 for all n greater than or equal to capital N. Therefore, the point will certainly belong to the limit inferior set. Since it will belong to limit inferior, it will also belong to the limit superior, and limit superior cannot be bigger than the interval 0 1. Therefore, it is also equal to limit superior, and therefore the limit of the sequence exists, and it is the open interval 0 to 1. Let me complete today's lecture by giving the final exercise. Let us consider a sequence of defined by that d1 is equal to E1, d2 is equal to d1 delta E2. In general, dn is equal to dn minus 1 delta En for n is equal to 2, 3 and so on. Show that the limit of the sequence dn exists if and only if limit of the sequence En is equal to 5. In next class, we will introduce the concepts of certain algebraic structures such as rings, sigma rings, fields and sigma fields, which are eventually going to be used for the definition of a probability function. Thank you.